All right, good morning. It's my great pleasure to introduce Dr. Ismail Alkhouri. So Ismail is currently a research scientist at Los Alamos National Lab. So actually, he just joined the lab. So this week he's visiting, actually today, this whole week, he's visiting Los Alamos site. So that's why I can't make it in person. I really hope to get him on site, but unfortunately. But anyway, so he is at the same time also affiliated with University of Michigan as a military scholar. So we work in this lab called, you can see from the slides, like Michigan SPARC, which is basically a collaboration between University of Michigan and Los Alamos National Lab. So they basically sit in University of Michigan and interact with the faculty, research scientists, and graduate students there. So Ismail is a very passionate and insightful researcher, and you can tell from the areas he works in. He works in quite a number of different areas, but interleaved kind of generative models, numerous problems, large-scale optimization, robust machine learning, and so on and so forth. And another thing I want to highlight about Ismail's experience is that he has, besides that Los Alamos National Lab, he has worked in a couple of DoD labs. So one of them is an Air Force research lab, and the other one is DARPA. So if you have any question about what these guys are interested in, or you want to start some project with DoD, I think Ismail is the right person to talk to. He's got super experience there. And the last but not least thing I want to highlight is that Ismail has got quite a number of honors over the years. One of them is the Rising Star Award in companies of testimony and learning, and then the other one is, so I suppose this one is from Michigan State University. It's basically alumni outstanding research award. Right? Okay. So without further ado, Ismail is your state. Thank you.
All right. Yeah. I'd like to thank Professor Jusan for this invitation. And today I'll be talking about differentiable combinatorial optimization at scale. So I'm currently, as Professor Ju said, I'm affiliated with Los Alamos National Lab, hosted at the Michigan SPARC, and also have an affiliation with the Michigan Institute for Computational Discovery and Engineering at the university. So today, first I'll define the two problems that are representative of graph combinatorial problems, and then try to convince you why studying them in this detail matters. Then I think an important part of these problems to understand exactly how previous approaches have tackled these problems. Specifically, since these problems have existed for some time and they are very, very well studied and formulated. This will be followed by our proposed formulation. We'll also provide some theoretical insights, and then we will propose our parallel differentiable solver for improving exploration, and this will follow by results. So the first problem we will discuss today is the maximum independent set. So in the maximum independent set, here we are given an undirected graph, and then the goal is to find a subset of nodes in the graph such that there is no edges exist between them. And of course, we need this set to be the cardinality of the set as large as possible. This is one of the canonical problems that was introduced by Karp in 1974. And an interesting property of the independent set is there is a dual problem called the maximum clique, for which you can see here that we were trying to find a subset of nodes in the maximum clique such that these nodes are fully connected. So there is an edge that exists between each node. So why we're bringing the clique here with set? I think the more important part is that it's the duality between the two problems. As you can see from this figure here, if we pick nodes V1, V4, V5, these you can see it's actually an independent set in the graph, in which also it is a clique in the complement graph. But moving on to the second problem is called the maximum cut problem, for which here the goal is to partition the set of nodes into two disjoint sets. Here I'm calling them S and S complement. And the partition needs to happen, or the partition takes place such that the number of edges crossing the cut is maximized. So this is also an NP-hard combinatorial problem from the same set that was introduced in the 70s. So why does it matter? Like why are we so these problems have been there have been many applications where these problems actually many applications that were modeled or formulated as finding a set in a graph or finding a cut in the graph. But in addition to that, combinatorial optimization or NP-hard problems have a very interesting property called reducibility among these problems. And we'll take an example in this slide here. So we defined the independent set here, and then we also showed that how the miss and the click are related. So in here, for what does this mean here exactly? It means like if my application is to find, the goal is to find a click in a graph, then we can immediately reduce the problem to finding a miss in the complement graph. So there's a rule that exists. If we find a solution for one problem, that we can map it to another problem. So another example for miss is the another combinatorial problem called the minimum vertex cover, for which the rule is given here in the arrow, and this also goes both ways. So if I'm solving and if my application is to find an independence in a graph, then I can use this rule actually to map it to, or move the instant, or reduce the instance to another problem, and then solve it there and come back. So these are the nice properties. Another also nice property that is kind of not graph related is the max3 sat, for which you can see here a direct rule or a direct reduction between the maximum satisfiability problem. We can actually reduce an instant, a max3 sat instant to a graph, solve the miss problem, and then there has been some theoretical results that showed a solution in the miss is actually a solution to the max3 sat problem. So this, in generally speaking, the reducibility is something that is, I would say, very useful and interesting in these kind of problems. All right, so for the maximum independent set and the maximum cut, how did previous solvers approach that? Or the first, and I think the most well-known, I would say, the approach is to formulate them as integer linear programs. And then integer linear programs have, I would say, like the main limitation is scalability in dense graphs. The reason being that these integer linear programs, the number of constraints in these programs is equivalent or is related to the number of edges in the graph. And the higher density in the graphs, the higher number of edges, then the solutions becomes harder to obtain. And when I say solution, for ILPs, I mean global optimality, so global solutions. So the best feature in ILPs is actually if I give the ILP enough or sufficient amount of time, we have guarantees that global optimality can be achieved. Now, the problem is in the practice, when the graph size and the edges increase, solving for the optimal becomes computationally very expensive. The methods that are known for ILPs, of course, I think many of you are familiar with Gurobi, and also the more recent Google OR tool solver, the constraint programming SAT solver. So these are very well-known CPU-based methods. And another approach that's been also ongoing development in the theoretical computer science community is the problem-specific heuristics, for which here the main limitation is also scalability in dense graphs, because these depend on many graph reduction techniques, and some local search that become not as effective when density of the graph increase. And another limitation of these is that here we do not have any optimality guarantees. It can run forever, but there is no guarantees that we will obtain the global optimal. Now, what is the best feature of these solvers is provides a state of the art on sparse graphs. And in terms of methods, I think the RadioMS and the BLS, the breakout local search, are the among the two most famous and well-known solvers for heuristic solvers for independent set and the click problem. I'm sorry, the MaxCut problem. Now, more recently, data-centric machine learning methods have also tried to approach these problems. And then I would say, in terms of limitations, there are many of them. They do not scale very nicely also in terms of number of nodes and in terms of density. And similar, I would say, to many machine learning methods, generalization is a challenge. In the case that I'm training with some set of graphs and then I'm testing with a graph that is outside the distribution of the training set. And then again, this is also considered, so we don't also have optimality guarantees with machine learning methods. However, I would say the best feature for these methods are we can obtain feasible solutions at inference very, very fast. So this is, I would say, the best feature of machine learning methods. Now, which techniques in machine learning? I know the audience here is a machine learning. So there has been, it's all over the place. There has been started with supervised learning with a graph convolutional network in 2017. And then many subsequent works focused on reinforcement learning, most famously the learning with the deferred method that I'm citing here in 2020. And also even more recently, there has been unsupervised graph neural network methods, which has the advantage that we do not need to label our graphs or training graphs with the true solutions. And also more recently, diffusion models have also been used to solve combinatorial problems. So in this case, we are giving a training set and we're trying to learn, we're trying to need some approximated distribution for which we can guide for solution at inference. All right, so moving on, how do people solve the maximum independent set? There's a very famous and well-known formulation. This is the number and integer program. And here you can see that we have two terms. For the first term encourages selecting as many nodes as possible, and the second term penalizes selecting any two edges. As you can see from the summation, we are summing over the edges of the graph. Now, gamma here is called the edges penalty parameter. And in matrix form, this function can be written with respect to the adjacency matrix that we term as AG. And then in 2012, there has been some theory that shows if we are to select gamma according to this bound, so strictly more than one, then all local minimizers of the MICDE, COBO being the quadratic unconstrained binary optimization, are actually binary and corresponds to independent sets, maximal independent sets. All right, so what do we do in this paper, which this we published in ICML last year. We do two things mainly. We relax the continuous, the integer domain to a continuous box constraint between 0 and 1. And also, again, we're going to bring back the duality between the miss and the click by introducing a third term here, which we call the click term, and then gamma prime here, we call it the click term parameter. And just to re-emphasize that the first term here in this reformulation or this formulation is encourages selecting as more nodes as possible, and then the second term we're penalizing selecting any two edges in the graph. However, remember every edge in the complement graph is actually a disconnect. There is no edge in the graph. So making use of the duality. So the third term here is I would say similar to the first, but it is based on the edges of the complement graph instead of the nodes only. Okay. Now, in matrix form, we can write this reformulation using the adjacency matrix and also the adjacency matrix of the complement graph. Now, what I want to say here that if we use this property that relates or that connects the adjacency of the complement to the complement graph, we can actually rewrite the formulation using an L2 norm and an L1 norm over X. And the main point of here I want to say is that this indicates that we have exactly the same matrix vector multiplication in the second term that is similar to the one without the click term. That tells me that the computational cost of running the quadratic formulation with and without the click term is actually the same. All right. So for the max cut here, so we're given a graph and then a Kubo quadratic unconstrained binary optimization for max cut is given by this optimization problem, and you can see we're trying to maximize the difference between the two these two x's here, the binary, and then of course we're summing over the edges of the graph. And now, of course, in matrix form, we can write this formulation with respect to the degree matrix D and also the Laplacian, the graph Laplacian L. So what do we do in the first? So this was an AI stats paper in this year. The first thing that we do, we introduce something called quadratic box constraint optimization, which is simply a relaxation from an integer domain to a continuous box constraint between where x is between -1 and 1. And so with this, of course, we call this optimization, or we call this formulation as KUKO. And then if we let z to be a binarized vector given by this function here, then the cut value is simply z transpose LZ. So there's something that I'd like to emphasize here between the difference between the miss and the max cut is that the max cut does not have a penalty, while miss has a penalty. So the max cut is I would say it's maybe simpler to solve because any subset of nodes give me a cut value, a valid cut value, while in miss, not every subset of nodes gives me a valid independent set. So the next thing that we do in this work for the max cut is we propose a lifted quadratic for optimization. And this is the main goal of this is to expand on exploration. Because again, here we do not have to worry about a penalty term during the optimization. What we call here LUCO, or lifted quadratic optimization. Here we represent basically every node by an L-dimensional vector. So in this case, we'll have a matrix X that is also bounded between -1 and 1, and with dimension of n by L. And the lifted version here is simply the trace of X transpose L times X. Again, the L here is the lifting parameter. So in LUCO, to emphasize, and so we're going from the unlifted, where the objective is simply a quadratic objective function between using a vector x. So we're going from unlifted, where you can see that we are actually if we're to solve, we're solving only one x, right? One initialization of vector x, and we're going to the lifted domain, where you can see that from the matrix on the right, in the lifted case, you can see each column here, it can be thought of as solving the unlifted case. So this is how doing this exactly in matrix form is equivalent to, each column is equivalent to actually doing the unlifted here. Now, the main difference and where the explanation comes from is that after running each of the L columns of matrix X, we obtain the cut value by actually summing for every node we sum the each row, and then we determine based on this criterion here, we determine whether this node is going to be in set S or its complement. All right, so for the theoretical insights, so let me start by this notation here is like, let me start by saying that this notation here corresponds to the update rule of X, where alpha here is the step size, and then the pi is the projection operator towards the box. And I'm using this notation here for the gradient operator because I want to be as general as possible. And this of course, so this G with respect to different objectives, F, G, and H. These corresponds to the miss, unlifted cut, and the lifted cut. And then also this can be with respect to different type of optimizers. So it could be gradient descent, momentum-based gradient descent, etc. Now I'm defining something here that is going to be important in the next few slides. I'm defining something called PGA fixed points. It's basically any points for which that satisfy this equality. So this equality tells me that if I am at vector X and I take a gradient step and I'm going to remain exactly at point X. So this is what I'm calling PGA. Although I'm using PGA, which corresponds to projected gradient descent, but this generalizes to other type of optimizers. So it's just a naming. So what are the questions we're trying to address, or we're trying to clear out for us to obtain the best optimization strategy as possible? So the first question is like, these relaxed reformulations are non-convex. So I'll show you how these are non-convex for both problems. And then we will show some conditions for which the local optima corresponds to binary points. And then at last we will give some insights on unwanted stationary points. So these are where the gradient gets stuck, or the optimizer gets stuck. For the first question, non-convexity. So let's look at the miss problem at first. So the miss problem, when we write this, the fixed Hessian basically that is defined by the adjacency and the adjacency of the complement graph is always a non-positive semi-definite. So since this is as simple as it gets, this is a quadratic optimization. Once we know this is non-PSD, then this is immediately a non-convex optimization. And of course, the way we prove it is as simple as testing some feasible some x's. So not all x's basically satisfy the positive semi-definiteness condition. Now for MICDE, things are a little bit different because the Laplacian for the graph is always positive semi-definite. So this tells me that this actually h of x here is always convex function. Now, and we showed this simply can be shown by the breaking down the objective function using a summation, and you can see that this condition always applies for any values of x. Now, then how is this non-convex? So it is actually not. It's not a non-convex, so it's convex. But so. However, since we're using projected gradient descent, so although the projection operator on H or G does not affect convexity, however, it creates boundary points that are inescapable by PGA, and that's why the MICDE problem exhibits this reformulation exhibits a non-convex behavior. Now, moving on to the boundary local optima. So in this theorem from MIS, we show that if we select gamma and gamma prime, that is the penalty parameter and the click parameter, according to this inequality, then we guarantee that all local optima of the of f of x are actually binary vector that sit at the boundary of our box or our feasible set. And then, of course, there are PGA fixed points. Now, for MICDE, the MICDE things again. I'll bring back. I want to emphasize that the MICDE we do not have a penalty, and every basically every subset of nodes give me a solution, and that tells me that any boundary point that sits like given as this Z is actually a local optima of G, except for the case of the all ones or the all minus ones vectors. And the reason is because of the null space of the Laplacian that I will talk about I'll talk about shortly. Okay, now for the MICDE problem, we want to see like, are there any stationary points, unwanted stationary points? I'm calling them unwanted because basically I'm trying to look at points where the gradient is equal to 0. Okay, and then in the MICDE problem, we saw that these may exist actually, but the main question becomes actually, are any of such points that I'm calling X prime, it's actually in the feasible set. So we found out that the existence of such points are actually depend heavily on the graph structure. And to give you an example of our exploration in this direction, I'm bringing up 4 graphs here. So let's look at here the y-axis is the value of X prime, and then the x-axis is the node index, and then the title of every plot here corresponds to a different graph. So let's look at the first top 2. So here we have an Erdős graph, 100 nodes, 100 nodes, and then P here is basically is the probability of edge creation, which indicates the density. So here we're going from dense to denser, from 0.6 to 0.8, and you can see that there is a unique point where this inverse exists. And then you can see that in both of these graphs are actually have values that is below 0. That tells me that these actually X prime sits outside the boundary, outside the feasible set, and we will never encounter them. That said, on a GNM, and if we look at the bottom 2 plots, and look at the GNM, which is also a different type of random graphs. So here we're going from dense to denser. And we can see with 3,000 edges, this still have node indices that is below 0. So this is outside of the feasible set. And the only one that we found that is super sparse, and I'm sorry, super
dense, because you can see that the number of edges here is 4,945, which is basically it's missing only 4 nodes, and it becomes a complete graph, which means that all the possible edges in the graph do exist. So only in this graph we found that this X prime sits in the feasible set. So empirically, we never really encounter such cases. Right, moving on. So now next we look at the unwanted stationary point for the max cut. So first I'll talk about the unlifted case, and then I'll move to the lifted. But a shared lemma between the two is again, I want to say something. Here we do not have a linear term. So if we are going to examine where the points of X or matrices X where the gradient is equal to 0, we're simply looking at the null space of the Laplacian. What we know, what a nice result, that if we have a one component graph, then the null space of L spans all the ones vector. And this is the reason why in the local optimal slide I excluded the all ones and the all minus ones vectors. Now, what does this null space tell me? This tells me that here, if we actually encounter any point that is C times the all ones vector, where C is between -1 and 1, then this is actually an unwanted fixed point, because in this case, if we apply if we compute the cut at this point, we will get exactly cut if equals 0. So this is an unwanted stationary point. And then for the lifted case, this same C actually extends to the matrix case, which is the first bullet points. And then the second case is when this is also an unwanted, because remember that we're actually computing the cut by summing every node, summing every row. And then if the sum of every row is actually exactly equals to 0 or 1, then this immediately, according to this rule, we will get a cut value of exactly 0. So we do not want to encounter such points. So in short, in summary of these theoretical insights, we have shown that these are highly non-convex quadratic problems, and then every independent set or cut is an unescapable PGA fixed point. So now the goal is we want to find, based on these reformations, or come up or with put together as optimization strategies that improve exploration and, of course, maintain efficiency and scalability. Because in combinatorial problems, I mean, we could think of really like a second order optimizers or more complicated steps. But I think the main target of our work is to actually come up with solutions that are very efficient and can scale nicely to large instances. So what do we do? The first thing that we do across the two problems is we use a projected momentum-based gradient ascent, which we empirically found to be more effective than vanilla gradient ascent. And more importantly, I would say is the degree-based parallel processing, for which we used GPUs so you can see here that the y-axis is this illustrative diagram. The y-axis is GPU parallel resources. The x-axis is the time. So you can see we solve multiple initializations in parallel in every batch, and we repeat this this process until time permits. Now, why do I call it degree-based? Because for MIS, we use this Gaussian, where the mean is obtained based on the degree. And the intuition here is that nodes with higher degrees, this means nodes with more connections, are less likely to be included in the set. A similar intuition is also used for the max cut, for which we use this bounded uniform distribution, where we know that higher node or higher degree nodes, when they switch from S to its complement, the cut value will have more impact. So here I want to emphasize that so we call this as the degree uniform initialization, DUI, not the nicest names, I would say. And then we also adopt something called important degree initialization. So both on the same, which we call IDI. So both will be included in our solver. All right. Now, specifically to MIS, again, I try to recap that MIS has penalties. And if you give me a set, the way I can evaluate, or if you give me a subset of nodes, the way I can evaluate whether this is actually a MIS or not, is the standard way is to iterate basically over all nodes and then check the neighbors. And then I tell you this is a MIS or not. Now, you can imagine that when like the graphs becomes super large, we are iterating over like 20,000, 30,000, 3,000, like a very large numbers. The way this becomes really costly and expensive to only check for MIS. Now, in our theoretical results, we showed that every local minimizer or local optima is actually binary and corresponds to a maximal independence set. So this tells me that a PGA step will only take me outside of the boundary. So it is a PGA fixed point. So in this paper, we actually came up with I would say a very efficient and effective way to check for MIS. So here let's take only two steps. The first step is to binarize any X. So it's a binary vector that corresponds to the set I want to test. And then the max is criterion here is I'm just testing, is this Z is at the boundary or not? And as long as it's a boundary, and all gradient direction takes me outside the set, the feasible set, then I can guarantee you that this is a maximal independent set. And I'll show you later on how effective this is when compared to the standard method. Now, what do we do for the maximum? Oh, I'm sorry, for the max cut. So remember, we introduced two objective functions, the cuckoo and the luco, which corresponds to the unlifted and the lifted. And so here we propose an algorithm that combines the two, basically to make use of the exploration or the efficient, I would say the efficient optimization on the unlifted, and of course the exploration that was the base of introducing the lifted to come up with this parallelized dimension alternating quadratic optimization or PDECO. And here, basically, again, this illustrative we'll start with cuckoo solving multiple initializations in parallel, and once we obtain the best, and then we sample each column to start this matrix X in a PLUCO, and we solve a number of parameters, and we repeat this process basically up until our time budget expires. All right. In terms of results, and I want to first say that this is way too many numbers, and I always hate when I get to this slide. So let me tell you. So the first column corresponds to the methods, and the second column corresponds to the type of the method. And then I'm testing two data sets here. One is a sparser than the other. One is called SATLib, and the other is called Erdos-Rainy. And then the other thing is that since I'm comparing with machine learning or learning-based methods, I'm highlighting what training data that was used for these results. So the last four rows corresponds to our method using different number of batches, and you can see in here I'm comparing with GCN, learning with the deferred, DIMES, and the FISCO. These are different solvers, and from supervised learning, reinforcement learning to also diffusion models. And as observed, or as can be seen here, we achieve better results in both. Of course, the miss size here, the higher the better, and then the runtime is the lower the better. So you can see that in all cases for SATLib and for ER, we achieve better results than all learning methods in terms of the miss size, all without requiring any training data. Now, in this slide, I show the comparison between here. I'm setting the gamma prime equals to 0. So this means that it's our algorithm, but without the proposed click term. And you can see comparing, like, for example, 412 and 423, you can see that the click term does actually achieve better or accelerated convergence. And a similar observation is seen for the denser graph when we compare 40 to 45 to 44. All right, so where do we stand from state-of-the-art heuristics and ILPs? And in the sparse graph, I can tell you with confidence that nothing beats the heuristics, and nothing beats ILPs. In fact, you can see that all the instances were obtained to the optimal. Of course, SATLib. These are SATLib. These are graphs that come from SAT problems. So we know the optimal in these graphs. So you can CP-SAT solve all the graphs in the SATLib in under 1 minute. So this is how impressive this is. And again, this is in sparse graphs. Now, if we go to denser graph, you can see that actually this is where our method actually perform better, even requiring less runtime. You can see that, for example, Groovy with 64 minutes obtained 39, and in our case, with 5 minutes, we obtained 44.5. Okay, so this also highlights in this plot, we highlight the runtime scalability with mid-density graphs. So, and here, the x-axis corresponds to the number of nodes, number of edges, and the average miss size. And the runtime is basically the runtime required to obtain this miss. And I'm comparing with RadioMiss, Groovy, and CP-SAT. And you can see that as the number of nodes and edges increase, all methods are either like go out of memory or cannot return results, or also RadioMiss will require significantly more runtime than our method. So you can see the scalability of our method. Now, that said, I have to emphasize that these three solvers are CPU based, and our method actually using a GPU. So this is, I wouldn't call it this as 100% apple to apple. All right, I introduced an effective way to check for miss. And in this result, I show how this impacted the runtime. So the x-axis, again, this is a graph size, and increases in the x-axis, and then the runtime required to run our algorithm with blue corresponding to the standard way, which again iterate over all nodes to check its neighbors, and then the green and orange corresponds to the mischecking that we came up with, or that checks for boundary points. And you can see that, for example, with the largest graph in this plot, we actually achieve a runtime that is less than half of what the standard way of mischecking requires. All right, moving forward, maybe I'll skip this result, and maybe I'll move to the max cut result. So again, I'm doing the same thing. Too many numbers. Here the numbers are uglier because the cut value is a much larger number. So here again, we have solvers. We have solvers in the first column, and then I have three data sets: a small ER, large ER. And then the GSET. GSET is a very well-known benchmark for max cut, but it's also very sparse. Now, small ER, these are like also dense, but it's a smaller number of nodes, around 700 to 800. However, the large ER here we're talking about graph with 20,000 and 30,000 nodes, with including 10% of the edges. So it is dense, definitely denser than the GSET. So the first observation I have is that I'm including Groovy and CPSAT. So these are the ILP solvers. And you can see for smaller graphs are actually nothing beats these two methods. They are very, very effective and in terms of cut and also the runtime. And also I want to include one thing here. I want to include the first solver, which is called the SDP plus parallelized. So there is a very well-known algorithm for max cut, approximation algorithm that guarantees an expectation 0.878 of the optimal. And I was thinking of like if we are using GPUs, and okay, so that algorithm requires sampling from the Gaussian, and then I was thinking of like, what if we use GPUs to sample from the Gaussian to accelerate this method? So again, this requires SDP solution. So it is polynomial time, but it doesn't scale nicely. So I'm calling PGW, that's a parallelized GW algorithm. So you can see the results within 16 minutes, actually, in the small ER graphs. This method not only outperforms our methods, but you can see that also it can outperform learning-based methods, which I'm including here. The learning with the defer, which is a reinforcement learning approach. NECSP, it's a reinforcement learning approach, and OpGNN is an unsupervised learning approach. So with a simple batching and SDP, we can actually achieve this algorithm achieves really, really good results. Now, when compared to these solvers, as we scale up, our method becomes capable of obtaining solutions. Now, again, when compared to learning-based methods, we do achieve better results. However, the runtime, as I indicated before, is faster in some cases, which is something that is a feature in learning-based methods. But when we go up to like very large ER graphs, only NECSP was able to return results. And also I'm including comparison with PyGNN and CRI. These two methods use GNN in a training data-free setting. This means that it's doing lifting over the graph neural network and optimizes over one graph. So for every graph, we optimize the whole parameter. So this method is maybe a little bit slow when compared to other learning methods. However, it avoids the potential generalization issues that may happen with learning training data-based methods. All right, so here also PQCO, PLUCO, and then these are the two initializations that we proposed. As can be seen, the PDECO algorithm, which combines or iterates over these two objectives, achieve the better results. All right, and this I show some convergence plots, and it can be seen that where NECSP and PyGNN can obtain early good results, eventually under the 200 seconds budget, we eventually achieve better results when compared to all the others. And to be specific, these comparisons actually, these are all GPU-based approaches, not only our method. All right, maybe I'll skip this and then, okay. So I hope I didn't bore you guys, and let's put back a summary or put back our solver that I've been talking about back to the same table. Like, so where do we stand among others, right? So let's look. So we talked about differentiable quadratic optimization. So in terms of limitations, while we provided some theoretical insights into the characterization or characterize these points, there's still no optimality guarantees, global optimality guarantees in our solvers. These solvers can be run forever without any guarantees. And also another limitation, I would say, for our solvers, it does require to obtain the best results. It does require like fine tuning few scalars like the step size or the penalty parameter or the number of batches so these does require hyper. However, I would say the best feature, as I hope that I convinced you, that we do scale up and in terms in the scalability, not only the number of nodes but also in the number of edges, which is something that many other previous solvers had faced challenges with. Now, the two methods that approach is the PCQO for MIS and the PDECO for MICDE. All right, maybe I'll skip this. And for future directions, I want to go from undirected graphs to directed graphs. One application can be the kidney exchange problem here. Here you can see that every node is a donor patient corresponds to a donor and a patient, and then the connections here correspond to compatibility. And there's a well-known long ILP to solve this problem, but it's known to actually scale poorly. So I'm hoping to maybe trying to come up with a reformulation and a continuous reformulation that can actually use some of the GPUs or first-order gradient methods that can scale up these problems. Another direction is also going from ordinary graph to hypergraphs. There are also NP-hard there. Hypergraphs is basically here we're allowing edges to contain two or more nodes. So also there are NP-hard problems that we can maybe address, getting insights from the works here. All right, in summary, so provided a differentiable reformulation for both problems, and we supported this with some theory, and then an important feature of our solver is it's training data free. Again, we do not face any generalization issues other than maybe tuning some hyperparameters. So empirically, we showed that we outperformed all learning methods. We achieved very good results when compared to SOTA heuristics on dense graphs, linear runtime scalability on denser graph for MIS, and better convergence than data-based and data-less method for MaxCut. I would like to emphasize again, highly sparse graphs, nothing beats Kurubi, CPSAT, or the state-of-the-art heuristic. So these are the solvers to go to if the applications require sparse graphs. And thank you very much.
Okay, thank you very much, Ismail. Questions? People on Loop and also, yes, Ari.
Yeah, thanks, Ismail, for the great talk. I just have a probably simpler question about the motivation. So a lot of the results were divided into sparser and denser graphs as the two classes.
Yep.
I'm just wondering, what are some applications where denser graphs arise very naturally, where I can think of for such problems?
Where denser graphs come out naturally. I mean, I haven't really looked into applications where denser graphs actually happen, but this is something that we wanted to do in order to really understand the limitations and capabilities of our solver. We wanted to see like where do we, and I think this is something that we do, but other methods maybe do not do as much. We do in the paper, we do provide a lot more results, and that was the way we convinced reviewers. So and in many of these, for example, for MIS, we had I think we included results on the DMACUS dataset. The DMACUS dataset is an older dataset from the early 90s, and this actually was a combination of, it was for the click problem, and it was actually a combination of graphs that were obtained from practical applications. So these were not graphs that are randomly generated. So to answer your question, I assume that there must be a lot of applications where this DMACS dataset were obtained.
Okay, yeah, thank you. And a quick follow-up on that is there a notion of finer granularity for how we talk about structure in graphs for these optimization algorithm, like beyond sparse versus dense? Is there other notions that I can divide them along these?
So yes. So there are, I mean, you know, in from what I have encountered in practice, like many graphs, they may not have a kind of a uniform distribution over degree. So here even when we say denser and sparser, we're considering random graphs. And random graphs, they have some so every node will have a very similar number of edges, right, in the graph. But in practice, and for example, the DMACS dataset, if you plot some of these graphs, you can tell that they could combine of like multiple subgraphs, or like something similar to the what's it called, the block the graphs with clusters. So I would say the DMACS maybe, and then also for MICDE the GSET. I'm very sure that these were obtained very similar way as DMACS, where they came up from like VLSI design or other applications. So yeah.
Yeah, thank you.
Yeah.
Other questions? Maybe I'll ask you one. So your algorithm is largely based on like projection style, right? Even your momentum warrant, I suppose that each step we do a projection onto the feasible set.
Yeah.
But you know, I think for constraint optimization, there's a empirical observation that, you know, if we in early stage especially, you know, if we force feasibility, that actually may hurt the performance in the sense that you may easily get stuck at some saddle point or you know, on the surface, right? On the surface of on the boundary of the feasible set.
Yeah.
So have you explored algorithms that are infeasible in the early stage at least?
I have not, and I would say that the reason is we never really encounter that empirically, and that in early stages we get stuck. And as I showed in the stationary points, if there exists some stationary points, they are actually depend on the graph structure, and it's only for very, very super dense graphs. So we never really, I think when the constraints become more complicated, but I think any type of other constraints are more complicated than the boxes. So definitely we have to explore other types of optimizers. Yeah. Yeah.
Any other questions? Yes, go ahead.
So on one of your slides, you said that the MICDE problem is non-convex, but I don't think you really proved it was non-convex, right? You showed that there was some unescapable fixed points.
Correct. So I actually the quadratic Laplacian, or the quadratic term, we have only one quadratic term, right? And the Laplacian is positive semi-definite always. So the function is actually convex. But since we are using projections, so and these projections create fixed points. So fixed points means if I keep applying the gradient, I'm gonna get stuck. So it's actually convex, but with the projection, I have a non-convex behavior. That's what it is basically. Yeah.
Yeah, I just have a curiosity. I'm very curious about this kind of problem we are talking about. The major bottleneck is come from the optimization, like it's better to find a good local basin, or from the modeling, like design a good relaxation.
So I think this question depends on the application. If you're, as I have emphasized, and like If your application depends on is going to boil down to sparse graphs, and I can tell you that ILPs and heuristics is the way to go. But once these become a little bit more dense graphs and a little bit more complicated, so let me give you an example. Like for example, RadioMIS, the heuristics in MIS depends on what's called graph reductions. So when the connections of the graph becomes more complicated, less graph reduction techniques can be applied. So this makes RadioMIS very hard to reduce the graph and then solve it. So in our case, when I would say a more complex connections in the graph, this is where the reformulations or the differentiable approaches can become really effective.
Any last question? All right. If not, let's thank the speaker again. Thank you very much.
Yeah.
And I hope you enjoy your stay with La Summer.
Thank you. Thank you. Thank you for the invitation. Thanks a lot.
Yeah.
Okay. Take care. Bye.
Bye.